Hello students, welcome to the concept spectrum of AM wave. In the last video I explained about the time domain representation of AM wave. This is the spectrum of AM wave, which is nothing but frequency domain representation of AM wave. Okay. See, what is the time domain representation? The time domain representation is S of t is equal to x of t plus AC of cos omega ct. Okay. So I'll write the time domain representation. What is that? That is S of t is equal to x of t plus AC of cos omega ct. Now, to get this frequency domain representation or the spectrum of AM wave, simply you have to apply the Fourier transform for this time domain representation AM wave, that is for S of t. Okay. Any case or in any application or in any concept, to get frequency domain representation of any wave, simply apply Fourier transform for that wave. So Fourier transform or Fourier series are used to get different frequency components or the frequency coefficients or the frequency information contained in that particular wave. Okay. So here also, to get the frequency concept or information about the AM wave, we have to apply Fourier transform for AM wave. Okay. So now the spectrum is, so how to get the spectrum of AM wave? Simply apply Fourier transform, that is f of S of t. Okay. Yes, this becomes S of omega. Okay, how to get it? This is simply by applying Fourier transform on x of t plus AC of cos omega ct. Okay, so now our aim is finding the Fourier transform of this term, this total term, which consists of x of t and also carrier signal. Okay, so now I'll take one by one. Expand. The first term is x of t cos omega ct and the second term AC cos omega ct. Okay, so this is Fourier transform of x of t cos omega ct plus Fourier transform of AC cos omega ct. First, I'll consider the first term. Fourier transform of x of t into cos omega ct. Okay. So that is equal to, yes, Fourier transform of x of t into, you can write cos omega ct as, in terms of exponentials, you can write it as Euler's identity. This is called Euler's identity. I'll extend here. Fourier transform of x of t into e power j omega ct plus x of t into e power minus j omega ct by 2. That is 1 by 2 of Fourier transform of x of t into e power j omega ct plus Fourier transform of x of t into e power minus j omega ct. What is the Fourier transform of x of t? That is x of omega. Okay. Then, what is the Fourier transform of x of t into e power j omega ct? There is a property in Fourier transform concept. If the signal in time domain gets multiplied with the exponential term, then the Fourier transform for this is the shifted version of the Fourier transform. There will be a shift in the Fourier transform. So that is simply, it is equal to x of, okay, how much is the shift? The shift is this much. that is x of omega minus omega c. Okay. And for the second term also, f of x of t into e power minus j omega ct is equal to x of omega plus omega c. Clear? So therefore, totally your Fourier transform of x of t into cos omega ct is equal to, yes, what is the total? That is half into x of omega minus omega c plus x of omega plus omega c. The Fourier transform of this first term. Okay. Now let us go for the Fourier transform of AC cos omega ct. Okay. Second term. What is the second term? Fourier transform of AC cos omega ct. That is equal to, yes, Fourier transform of AC into e power j omega ct plus e power minus j omega ct by 2. That is AC by 2 of Fourier transform of e power j omega ct plus Fourier transform of e power minus j omega ct. Okay. So how much it is? That is equal to, what is the Fourier transform of exponential function? It is AC by 2 of, yes, 2 pi into delta of omega minus omega c is an impulse function shifted by this term omega c. Okay, and its amplitude is 2 pi. Then next term, Fourier transform of e power minus j omega ct, that is again 2 pi into delta of omega plus omega c. Okay, so totally it is AC of, again you can take pi AC, yes, pi AC of delta of omega minus omega c plus delta of omega plus omega c. So this is the Fourier transform of second term. Okay, so that is the Fourier transform of first term and this is the Fourier transform of second term. So now I will write combinedly, that is S of omega is equal to, yes, first term, half of x of omega minus omega c plus x of omega plus omega c plus, what is the second term? Pi AC of delta of omega minus omega c plus delta of omega plus omega c. So this is the spectrum expression, Fourier transform of the AM wave. Okay. So if you observe this expression carefully, here what is x of omega? What is x of omega? Fourier transform of x of t. What is x of t? Is the message signal or the information signal. Okay. So here, yes, the spectrum of AM wave consists of the shifted version of the message signal along with two impulses which are also shifted. If you observe the shift, there exists plus omega c and minus omega c. Okay. What is actually omega c? Omega c is nothing but frequency of the carrier. Okay. So now I plot this spectrum. I'll plot the frequency domain representation along with the previous time domain representation. Okay. See, this is the spectrum of AM wave. Here say, this is the Fourier transform of our message signal x of omega. Corresponding to this spectrum, this is our time domain. We already know it. This is the time domain representation of our message signal. This is the frequency domain representation. We are assuming that our message signal is a band limited signal. Band limited signal means it exists only in certain band of frequencies. Here in the communication band means frequencies, range of frequencies. Okay. So it exists only in the interval 0 to omega m. And remember, in the in maths, you have no negative frequency. Okay, actually. But when you apply Fourier transform for any signal, you know the Fourier transform consists of negative exponential. That is the reason we are getting negative frequency also. Okay, that is for mathematical convenience only. In real, there is no negative frequency. So, while analyzing or while calculating the bandwidth or while calculating the power, what it may be, we will consider only the positive frequencies. And other point is the negative frequency side is exactly the reflex of the positive frequency. Okay. So with these points, I'll explain the spectrum. So this is the Fourier transform of the message signal. And we are assuming it as a band limited signal, means it exists between 0 to omega m only. And this is C of omega, which is the Fourier transform of C of t. Okay. And see, yes, the Fourier transform of C of t is, this is, and yes, I have to write that expression. What is it? S of t? Sorry, S of omega. S of omega is half of x of minus omega c plus x of omega plus omega c plus pi ac of delta of omega minus omega c plus delta of omega plus omega c. Okay, so this is the expression. Fine. So this term is, the second term is completely the Fourier transform of the carrier wave AC cos omega ct. Okay. So now what is the Fourier transform of AC cos omega ct? It consists of two impulses at omega is equal to omega c, means at omega c. At omega is equal to minus omega c. Yes, this is the minus omega c. Here is the impulse. The two impulses amplitude is pi AC. Okay. So this is pi AC. Totally, if you see the S of omega, see here. What is the first one? The first term is, consists of shifted version of the message signal followed by shifted version of the impulses. Both shifts are same. If you observe, both shifts are same. Okay. So this is the S of t signal. Okay. You know this concept I explained in the last video. Now for this, see here. First draw the impulses at omega is equal to omega c and omega is equal to minus omega c. These are the impulses. And the message signal shifted versions are at omega c and minus omega c again. Okay. See, this is the message signal. And this is another message signal. Okay. And the first one is at omega equal to omega c and the second one is at omega equal to minus omega c. Fine. Okay. So both shifts are same. Both impulse and message both are existing at same frequencies. Okay. So this is the concept. This is the wave. Fine. So now, see, this is the center frequency of your message signal and you know the width is omega m. If it is 0, it is omega m, but this is omega c. So that is the reason this end is simply omega c plus this omega m. That is the reason it is omega c plus omega m. Okay. And then what is this minus omega m? If the center is 0, it is minus omega m. If the center is omega c, it is omega c minus omega m. Okay. Move to the negative frequency side. In the negative frequency side, we have impulse at minus omega c. And this is our message signal. You'll see these ends. What is this value? This value is omega m. So that is the reason it is minus omega c plus omega m. What is this value? This is minus omega m. Already the center frequency is minus omega c. That is the reason it is minus omega c minus omega m. Totally, this is the spectrum of your AM wave. Okay. So these are all the amplitudes. The impulse amplitudes are pi AC. The messages amplitudes are half. Okay, here also. Now if you observe, this is the carrier frequency. With respect to the carrier frequency, your message is occupying greater than the carrier frequency side. You are seeing one band greater than omega c, means there exists frequencies greater than omega c in the spectrum of AM wave, that is called USB. So what is USB? USB full form is upper sideband. Now, this portion, these frequencies are lying below the carrier frequency. That is the reason these are called LSB. Means this is called LSB. LSB is nothing but lower sideband. Upper sideband and lower sideband. What is upper sideband? The band of frequencies which are lying above the carrier frequency are called upper sideband, and below the carrier frequency are called lower sideband. In the negative frequencies side also, greater than minus omega c are called upper sideband, and less than minus omega c are called lower sideband. Okay. So this is the spectrum of AM wave. So now if you observe a spectrum, you have the message signal only at this portion. Fine. Because we are not going to consider this while calculations of the bandwidth or the power or etc. etc. We will consider only this. In this also, see this. This is from this. Actually, there is no negative frequency in the message signal also. Means the message is only between 0 and omega m. So in future classes, we are going to analyze it also. Then see this message. It consists of both sideband USB and LSB. But this we are not considering, and this is same as of this. Then what is the need of considering this? Okay, this we are going to analyze in future classes. So totally for this class, say this is the spectrum of AM wave. Okay, so now what is the bandwidth? Bandwidth required for AM wave. Okay, the bandwidth is USB minus LSB. So what is USB? Omega C plus omega m. What is LSB? Omega C minus omega m. So totally it is, what is the value? Yes, it is 2 omega m. So bandwidth is 2 omega m. Okay. So to send the AM wave, AM modulated wave, to send amplitude modulated wave, if the message signal frequency is omega m, we need 2 omega m bandwidth. So that is the conclusion from this spectrum of AM wave. Okay, thank you very much.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.